Welcome! In this video we're going to talk a little bit about the adidas assignment, the last assignment of programming in C and the assignments on which you will be assessed at the end of this module. Before we're going to look at the adidas assignment itself, let's first look at bit manipulation, because the adidas assignment is really based on working with bytes and manipulating bits inside that byte. In the C language, we have several small types. We have ushorts, unsigned short, unsigned chars, but we also can use the type uint 8_t. And this one is just saying I have an unsigned integer of 8 bits. So in fact, this is a byte. So an unsigned integer of 8 bits. You can also have 16 bits or 32 bits. Just check it out. So let's say we have declared 3 bytes named A, B and C. Then we can just give them values, and in a bit manipulation assignment we hardly ever use the decimal notation, like this one, A becomes 7. A binary notation, that's very difficult to keep correct, to avoid errors with all those zeros and ones. So normally we will use a hexadecimal notation. So 0x stands for this next number is going to be interpreted as a hexadecimal one. So the 0 is for the first nibble, so in this case 4 zeros, and the 7 is for the next nibble. So in this case 3 ones, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So that's 1 plus 2 plus 4, 7. Another example, B is 17. And if you immediately think in hexadecimal views, and you know that a hexadecimal goes from 0 until and including 15. F is 15. So if we have 17, that means that we go 1 times 16, 1 into the high nibble, the most significant nibble, and then we have 1 left for the least significant nibble. So that would be this representation, and in a hexadecimal way, 0x, 1, 1. And it's good if you practice a little bit with looking at this one, because it really helps you with the adidas assignment if you can orient in a hexadecimal way. Another example, C is 15. Okay, hopefully by now you say, oh, I know that one. That means the most significant nibble is 0 and the least significant nibble is completely filled with ones. And in a hexadecimal notation, 0x, 0f. And so this one you will use quite often in a masking of your nibbles. Okay, we can do some bit operations in the bit manipulation world, and of course the most simple one is the bitwise AND, and that's just one AND, and if you look at the logical AND, that would be 2, then we have a logical AND, but in a bitwise AND we only use one of the 2 symbols. So if I would do a bitwise AND with A and B, then what would the result be? So we all know the AND, that means we have 0, 0, 0, 0, 0, 0, 0, 1. So only the last position has both ones. So that would mean a hexadecimal value of 0, 1. And if we do, whatever, A and C, and then you immediately see the use of masking with something like this, because then the first nibble will become 0 and the last nibble will just take the vision of the first element, because this will not change anything of this nibble of A. So if we would work with a hexadecimal view, then immediately I would say, okay, I know this one, that the 0x, the first one becomes 0 and the second one stays as it is. So for another example, if I would make a bitwise AND with, for instance, 0x 3, 1, And I would do that one with this C, where we know the first nibble will become 0 and the second one will not affect the first element. Then that would give us 0x 0, the 3 disappears and changes into 0, 1. And so this is a nice way of masking one of the nibbles. We can also do a bitwise OR, quite straightforward. So if I have A or B, then I would get 0, 0, 1, 0, 1, 1, 1. So that would be 0x 1, and then the other one would be 7. So just a simple OR. A nice operation in bit manipulation is the exclusive OR. And we draw that one with this strange hat, exclusive OR. And for those of you who have had math from me, they would know how I explain the exclusive OR. And so, for instance, I have a colleague. This is a real story, by the way. I have a colleague, and this colleague of mine is married. But he also has a girlfriend. And of course, the two are not allowed to know from each other. So, when this colleague of mine goes to have dinner, then he goes with his wife or with his girlfriend. That is the exclusive OR. He will never take both at the same time. So if I would look at exclusive OR A, exclusive OR B, then I would say, okay, this one becomes a 1, because it's 0 or 1. That's an exclusive one. Then we have these two are also exclusive, but the last one are 2 1s. And that won't be a 1 in an exclusive OR, in contradiction with a normal OR. Okay, and then we can also do shifting, which is quite straightforward. For instance, if I shift A2 to the right, that means that these 2 ones here will just disappear and be moved off the byte, and it will be padded with zeros at the beginning. So you will not have a cyclic shift. So what will happen is everything is moved to the right. So we have only 1 left. Then let's look at this exclusive OR a little bit closer, because it's also a very ideal one to flip bits. And in the Adidas assignment, the second program you need to make is a program where you throw some noise on bytes. You flip bits, in fact, and you can do that with ideally with an exclusive OR. So if we have this mask, mask is 0, 1, 0x10, that means that on this position here, whatever is there with the other byte I'm using, it will be flipped. So if there was a 0 then, and we do an exclusive OR, then 1 exclusive OR 0 will become a 1. And so this 0 will change into a 1. If there was a 1 there, and I do an exclusive OR with this 1 and this 1, then it becomes a 0. So now the 1 is flipped into a 0. All the others will stay as they are. If you do an exclusive OR with a 0, then it means if there was a 1, it stays a 1. If there was a 0, it stays a 0. So the effect of using a mask with only 1 bit as a 1, then it will make the position of this bit flipped in whatever I'm using it for. So in num1, this one will be flipped. So we will get 1, 1, 1, 1, 0, 0, 1, 1. And in number 2, the same bit will be flipped. So I get 0, 0, 1, 0, 0, 1, 0, 1. So ideal to use as your channel operator. And by the way, it's also ideal to calculate parities. Okay, for the Adidas assignment, you need to make 3 programs. 3 programs. All of the programs need to have 2 arguments. So if we look at the first program, you need to encode what is inside a file and then write it to another file. what's in this file A can be a text file, it can be a file with pointers, it can be a file with struct, so any type is possible. So when you read from this file, you need to use bytes. When I'm testing it, I will of course use text files because otherwise I will not be able to check it. But in your program, you should not worry about what's the content of this file A. Just look at it as bytes. And the same you will do with the channel program where you throw noise on the files, and the decode where you try to restore it again. Okay, if we look a little bit closer at the first program, the encode, then we have several steps. First step is just read a byte. So you can already visualize that you open the file for reading and you read byte by byte and process byte by byte. First step in the processing is split up the byte you read. So let's say this is your byte. Then you have a nibble here. Let's call it a nibble, most significant nibble. And you have a least significant nibble. You split it up into 2 bytes, where on both bytes you have the data elements on the same position. And so this byte here is changed into 2 bytes where you put the most significant nibble on the right or on the left. That's your choice. Just put them wherever you like, as long as you split them up in 2 similar nibbles. Then you need to process. So individually you process each of these bytes which contain 1 nibble and you write it to the file. Okay, and how should you process it? What we want you to do is add parity to the nibble so you can do error checking when something goes wrong. As a hint, only use bytes, and beware, efficiency and memory usage are important. Okay, how should we process each nibble? We have 4 data elements. So if I would use the representation I did in the previous slide, then this would be D0, D1, D2, D3, and this is empty. And we can add elements there. Okay, these data nibbles are put into a cycle structure. And what we need to do is calculate parity bits. So, for instance, this parity bit 1 should be 1 if these 3 elements together are odd. What I want to do is make the circles an even parity. So, for instance, if these are my 3 circles, and the data bits are like 1, 0, 1, 1. Then this parity bit here should be 0, because then this circle has an even parity. We have 2 1s. This one should be a 0. So this circle has an even parity, and this one should be a 0. Okay, let's do one change. So let's, for instance, throw this one out and make this 0. Okay, that would change this parity because now it becomes 1. This one will stay the same and this will change also into a 1. So I hope you get the idea of this parity adding. And then you need to store them in a byte, and you can do it any way you like, but in the study guide we suggest this storage, so where we use the data bits. So first we have 1 bit hasn't got a play in this complete procedure. Then we have the data bits, and then we put in the parity bits. But you can also put the parity bits on the left. I really don't mind as long as you're consistent in that. So for every byte you produce 2 bytes. For each nibble, 1 added with parities. Okay, thanks for watching the videos. I hope they were of use of you. This is the last one in Programming C1. So I hope you can manage to do the Adidas assignment, and just contact me if you have any issues or any questions. Okay, see you with the assignments.